Okay, so here's our last bit on chapter 6. And moving on from the previous lecture, we have the root mean squared velocity here, and we've mentioned this before. And here's the derivation, and the root mean squared velocity is 3RT over molecular weight. And we have to use the R value of 8.314 joules per mole Kelvin for this. And I'll show you this in a second. So why do we need a different value of R? Let's do this. Root mean squared velocity of oxygen molecules at 25 degrees Celsius. Okay, so let us do that then. So the root mean squared velocity, 3RT over molecular weight. So 3R, R is 8.314 joules per mole Kelvin. Temperature is 298 Kelvin. All over, now I'm going to use 0.032 kilograms per mole. All to the 1/2 power. So let's look at the dimensionality for this. So you're like, why are we doing this? The units don't make any sense. Let's look at, so D is for dimensionality. So we have joules per mole Kelvin times Kelvin divided by kilograms divided by moles. So you can see right away Kelvins cancel, 1/moles cancel, and we are left with joules over kilograms. It's the 1/2. So a joule is a kilogram meters squared per second squared divided by a kilogram. So you can see now these kilograms go away, and we're left with meters squared per second squared square root, which is meters per second. So that's the reason why we have to put those in. We have to use the joules per mole Kelvin, and we have to do the molecular weight in kilograms per mole. And doing all of that, you find out that the answer is 482 meters per second. So that's really fast, right? So that's really, really fast. Why is that? I mean, you think the air is moving that quickly? And this is the average. I mean, from the distributions before, some are not moving at all, and some moving faster. But this is about the average of them. And first of all, you're like, well, that's obviously breaking the sound barrier. The sound barrier is much smaller than at this temperature. Why aren't we hearing sonic booms? Well, because that would be macroscopic versus microscopic. So sound waves are little pressure waves that come away from things and go through the air. You have to have a large object go through it that actually would break the sound barrier for that. The other thing is, think about like, wow, I'm being smacked by oxygen molecules that are going this fast. Why can't I feel it? Like, well, you can feel it, and that's pressure. That's the atmospheric, among other things, that's the atmospheric pressure. The thing is, oxygen molecules are very, very light. But if you are hit by a huge number of them at the same time, then you can feel it, and that's the pressure. But also the pressure is equalized between your body outside and your lungs. Okay, so recap with this one. I should do a recap. What's the root mean squared velocity of oxygen at 25 degrees Celsius? We use the equation 3RT over m, square root of that. And we use the units 8.314 joules per mole Kelvin for R and 0.032 kilograms per mole. Why do we do that? Because of the units as seen there to get meters per second, and we find out it's 482 meters per second. Okay. So I mentioned that about gases, that they're really light and they fly around. And here's this picture You can see a gas particle starts, it goes pew, 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 pew. It's all hitting around, and they're moving very fast. It helps you if you make that pew, 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 pew sound. It actually has been scientifically shown to make this more interesting. But that and the collisions hits the walls, hits whatever. Maybe the air is in your lungs. Maybe it's outside of you. It's hitting your body. That little bit of momentum that the gas particles have when they hit you, that's the pressure. So gases, they move very fast and they fly all around. Uh, and then there's another phenomenon called a fusion. So maybe you've noticed that if you have a balloon, let it sit for a while, the balloon just kind of deflates. Why is that? Well, the gas diffuses out through tiny cracks. And of course, we have these metallic balloons seem to last a little longer. When I was a kid, we had the rubber balloons, and they wouldn't stay afloat for very long, but the metallic ones seem to be a little better. And it's Graham's law of fusion. The rate of gas A over the rate of gas B is the square root of the molecular masses of the second over the first. So the first related to the second is the square root of the rate of the second over the first. And why is that? Because of the velocity is square root of 3RT over the molecular weights. The 3RT go away and you're left with the ratio. And this is a way you can separate gases. So this one here, an unknown gas fuses at a rate that is 0.462 times that of nitrogen gas. So calculate the molar mass of the unknown gas in grams per mole. So the rate is 0.462 and rate of A over B. This is equal to the mass then of so it's going to be nitrogen. So N2. It's going to, okay. Put in the numbers here. Nitrogen is 28 grams per mole. So we have the square root of 28 grams per mole over our unknown mass. So what do? We square both sides, and then we multiply by x, multiply by 0.462. So you square both sides, you get 0.462 squared equals 28 over x, and then x equals 28 over 0.462 squared. And you put that in your handy dandy calculator and you get 131, and the units are grams per mole. So 131, and that's probably xenon. So xenon is 131 grams per mole. It could be something else, but it's probably xenon. So, and xenon, it's pretty heavy gas. Okay, so why do we care? This is one of the ways that we purify uranium. So if you've ever heard of depleted uranium is uranium-238. So if you dig uranium up from the ground, it tends to be about 0.7% uranium-235, and then the rest uranium-238. And we enrich it somewhere between 3 and 9% uranium-235. The odd number is the fissile fuel for nuclear reactors. So here in the United States, we typically enrich it to 3 to 9% in that range. Weapons grade plutonium needs to be 90% or higher. And right now, well, I guess I shouldn't talk about politics. Anyways, it takes a lot of energy to do this, and it's really hard to do. So how do we do this? Uranium is a metal. It's very high melting point. So how do we make it lighter? We use uranium hexafluoride, and this is known as yellow cake. This has a much lower boiling point, and you boil it and use a fusion, use centrifuges, and it slowly diffuses, and then over time you get more and more uranium-235. So how do you do this? So the rate of uranium 235 hexafluoride versus uranium 238. Sorry, let me make this a little prettier for you. 235, 238 hexafluoride by Graham's law of fusion is going to be the square root of, so 238 for the uranium plus 6 times 19, 235 plus 6 times 19 for the other one. And you take the square root of that, and you find out that it's 1.004. So it's very, very slight, and it's really hard to purify uranium. It takes lots and lots of energy. So why would you do it? You do it for nuclear power. But nuclear reactors, we enrich them only to about 3%. Usually we can go a little higher, but maybe as high as, like I said, as high as 9. Depends on the reactor. It really depends on the reactor. We don't have a set nuclear reactor type in the United States. We're really weird about how we do our nuclear power. But 3% is typical. It's just cheaper. It's cheaper to have that because a reactor core is about the size of a car or a couple cars. And I mean, if we double the size of the core, that's not that big of a deal. If you enrich the fuel more, then you can get away by having a smaller core. And having a smaller core on a civilian power plant is stupid. It's just a waste of money. We do have applications for high enriched uranium. We use it on our Navy vessels, especially nuclear subs. The nuclear reactors on the aircraft carriers, they have a little more space there, but they still use highly enriched uranium. Submarine, though, really the core there is really small, on the order of liters, rather than cubic meters that we have in a civilian plant. That's just because in a submarine space is a valuable commodity. Also, we're looking at sending space probes out. We want to melt through, using nuclear power to melt through some of the moons, the exomoons, I should say, or whatever, the other planetary satellites, to see if there's life there. And it's got to be nuclear powered. That's the only thing that we have, and that'll be highly enriched uranium. Also, of course, nuclear weapons need highly enriched uranium. But yeah, so as far as nuclear power is concerned, having a highly enriched uranium is really just a waste of money. So think about that. Okay. All right, but let's talk about real gases. This is not on any test. So you can turn your brains off if you're worried about getting too much information in. But we talked about ideal gases. What's an ideal gas? One that has the particle size has no volume of the gas. The gas has a volume, but the gas itself has no volume. There is no attraction whatsoever between the gas and the containers at all. But if you look at an ideal gas and then the molar volume of the ideal gas, so comparing at standard temperature and pressure for gases, which is 0 degrees Celsius, 1 atmosphere, that you can see here, helium is just about as good as you can get. So they behave that way. And then there's some non-ideal behavior, the effect of the particle volume. So because at a high pressure, the particle volume takes into effect, so the pressure is slightly higher. And then the effect of intermolecular forces, that's how the attractiveness between them, as the temperature gets cooler, the pressure goes down. So because of the gases tend to hold hands, and instead of two particles, they act like one. So there's the van der Waals equation here. The book talks about. Truth be told, there are better ways to do it than the van der Waals equation. There's the K's law is one of them. You're not going to learn about it in this book. There's engineering ways. There's also something called the Cox charts, COX, Cox. You can look up real data that way. And you can just use there's a lot of data on this. There's real data for things. So, yeah, there's better ways to do it, but the book talks about this, so I thought I'd talk about it. But I'm not going to test you on it, and so don't worry about it in that regards. But the point of this, though, is to let you think, oh, what's an ideal gas? What does it mean? What is a non-ideal gas? This is the point that I was trying to make of that. Okay, all right, well, on to thermochemistry.